Hey, thanks for checking out this video for going over atomic orbitals as a part of general chemistry review series in our organic chemistry class, Chem 211. And hopefully, like we said, that this is just going to be a review for you. You might recall in your general chemistry class discussing about where electrons actually reside, and they don't actually reside in like these orbits, kind of like the moon goes around the Earth, a very set pathway. Like there's just one path that electrons take. It's not like that at all. Electrons do indeed sort of fly around the nucleus of an atom, but they do so in a pattern that is referred to as orbitals. And orbitals are kind of like orbits, but except that they define a region instead of like one specific pathway or one specific path, and it's in that region that these electrons may reside. It actually describes level of probability that these electrons actually reside in these places. And the closer the orbitals are to the nucleus, usually the lower the energy level of that orbital. Okay, and so the lowest energy orbital, the easiest place to place an electron. And then you can imagine that would be the lowest energy, because electrons like to be close to the nucleus anyway. So it's not that hard to put electrons close to the nucleus, which would be the 1s orbital, which is the smallest and the closest orbital. It's a spherical orbital. And the 2s orbital, which is one energy level higher than 1s, has a little bit of a node in the middle. So that's that white node that you see in the middle of that picture there. And remember that each orbital can be occupied by 2 electrons, because 2 electrons can actually be spinning in opposite directions. So even if 2 electrons occupy the exact same orbital, they're not like totally occupying the same quantum space. So why can't it fit more? Until you take quantum mechanics physical chemistry classes, I would just leave it at the Pauling exclusion principle. Remember, 2 electrons cannot have the exact same set of quantum numbers, like the energy level, the orbital type, and the spin direction. If they're all the same, they occupy the exact same space, and you cannot have 2 electrons that occupy the exact same place. So but because there's 2 spin directions, 2 electrons can occupy an orbital. The 2s orbital is filled next, and then like we said, 2s orbital has a node right there, that white space. Now, once the 2s orbital is full, of course, because there's atoms that have more than 4 electrons, 1s and 2s together only fill 4 electrons total. So once that 2s is full, remember, electrons have to be in a little higher energy orbitals, and those are the 2p orbitals, which is still in the second energy level, we would say, but they're slightly higher than 2s, and they have these odd lobed shapes. And when you look at this first p orbital that you see on the left, 2py, I just want you to notice that is actually one orbital. It's not 2 orbitals of 2 colors that we're showing here. It's one orbital made of 2 nodes. What is a node? Well, remember, node is where the or I should say 2 phases, I should say. It's one orbital made of 2 phases that's separated by a node. Remember, node is where electrons cannot reside. So that's when, like, the quantum mechanics equation is solved for an electron, that it describes a probability of 0 existence at the center. That's the node. And then we're just using blue and red as two different colors to show the phases. And phases have to do with, remember that electrons behave kind of like waves. And when you look at a wave functions like sines and cosine functions, they can be either positive or negative. It has nothing to do with charges, but it just has to do with the phase of the wave, whether up and down, that sort of things, right? And then remember that you have three degenerate 2p orbitals. Degenerate orbitals just mean that they have the exact same energy levels. Whether an electron occupies a 2py or 2px or 2pz p orbital, they would be at the exact same energy levels. So, so total, you could have up to 6 electrons in p orbitals, because 2 each, right? And so here are some common ways of describing electron configurations for some of the earlier elements in the periodic table that you might remember practice writing back in Gen Chem, right? And then you start building these by using Aufbau principle. That just means the electrons fill from their lowest energy and on up. So you start it with 1s orbital and then the 2s orbital, and then you start filling the 2p orbitals. But when it comes to the p orbitals, there's 3 degenerate or same energy level orbitals, so you have to use the Hund's rule. Hund's rule says that you, let's say when you get the carbon, boron, maybe it's easier to understand that 5th electron would have to go into one of the 2p orbitals, so that's easy enough. But when you look at a carbon, we might think that the second p electron might go into the same orbital as the first one, so that the 2 electrons would be paired. Instead, those 2 p orbitals, 2 p electrons actually occupy 2 different orbitals, and that's called Hund's rules. It's kind of like, when you get on a public bus, you notice that most seats are like love seats. There's 2 seats for everybody to sit at, and unless you're kind of like a weirdo person, right, like you would not go sit next to a stranger that's already sitting in one of those love seat situations. You would go find a different set of love seats, or like different set of seats where you can be kind of sitting by yourself, not sitting right next to another stranger if there's other seats available. The same rule applies with electrons. It's not like they want to always cozy up to other electrons. So if there's another same energy level orbital is available, that's what it occupies. And so that's why you see in the nitrogen configuration, there's 3 electrons occupying 3 different 2p orbitals. But when it comes to oxygen, you'll notice that the 4th p electrons has to be paired up with one of the earlier electrons and so forth. And that, remember, is called Hund's rule. And again, any of these, if it sounds totally foreign, I would really encourage you to go and look at your general chemistry textbook or notes, which might explain some of these things in a little bit more detail. And remember, we said that electrons really kind of have like a particle properties, but they also have like a wave properties. And that's why we were talking about phases, ups and downs. But because they behave like waves, there is such thing as constructive interference. That's when the 2 waves of the same phase collide together, then you get like higher, bigger amplitude of a wave. The wave is enhanced, is what that means, constructive interference. Whereas destructive interference is when the waves of 2 different phases come together, then they sort of destroy each other and create a node, meaning like there's going to be a spot where there is no wave at all. And that's sort of how electrons work as well. When constructive interference happens, there results a bond. Why? Because at the middle of that wave is a high amplitude. Well, so that's another way of saying that's a big wave. Remember, wave function describes how likely it is that an electron exists at that spot. And if you get a big wave, that means there's a good probability that there's electrons at that spot. If that happens between two nuclei or two atoms, that's a good thing, because two atoms would be bonded together by those electrons. Because remember, if you think about two nuclei or two atoms, they don't have anything to attract each other with. Nuclei only have protons, which are positive. They repel each other, so two atoms usually they want to repel each other. They have no interest in bonding with another atom. The only reason why they do, as a concession, bond with each other is because there's electrons in the middle, right? So constructive interference, good. Destructive interference means there's no reason for two atoms to be bonded together. We call that anti-bonding. Whereas constructive interference situation, that's a bonding situation, which we also could explain that with molecular orbital theory back in Jenkins, right? Molecular orbital theory as opposed to valence bond theory, which only just focuses on like what's going on with the electrons and where they spend their time. Molecular orbital theory says if you mix in atomic orbitals, you always get the same number of molecular orbitals as a result. For instance, if you mix two atomic orbitals that have one s orbital each, you get two molecular orbitals, and one of those would be bonding, the other would be anti-bonding. Molecular orbital is an orbital that sort of extends over the entire molecule, not just like localized between two atoms. So if you have a bonding molecular orbital, we're saying that the electrons can exist anywhere in that orbital, whereas anti-bonding molecular orbital, electrons might exist in those two lobes, but not in the node in the middle, which means the electrons would not be bonding because they're not hanging out between the two nuclei. Can't remember if I included, oops, this fixture. Nope. So anyway, the number of molecular orbitals that are created as a result of mixing atomic orbitals, that those numbers being the same, remember that that's called a linear combination of atomic orbitals. That's the math you have to use in molecular orbital theory. And here's an example, other examples of molecular orbitals. The example B is kind of a complex one, but it's extending over the whole of molecule. Okay, but this is one orbital. Just has different lobes, but it's one orbital. I just want you to know. And also the example A shows one orbital. It's not two orbitals, it's one orbital with two lobes. Okay. And with all this background, it's probably self-explanatory to answer these questions, like why is the anti-bonding orbital higher in energy? Because it's higher in energy because there's no benefit in putting electrons in that orbital. In fact, it would not contribute to bonding because the electrons are not in the middle attracting the two positive nuclei. So there's no energy benefit there. And that's why for like hydrogen molecule, there's no electrons in the anti-bonding molecular orbital. If you ever wondered why is it that you cannot create dihelium molecule, and it's because helium comes with 2 electrons each, so CHE2 would have to have 4 electrons total. So the first 2 would go into the bonding molecular orbital. Remember Aufbau principle, it works just like that. And then the next 2 electrons would have to go into the anti-bonding molecular orbital on the top if you mix 2 helium atoms that comes with 1 s orbital each. Now those second set of electrons second pair of electrons that have to go into antibonding molecular orbitals that destabilizes this molecule because those electrons are antibonding. And for that reason, that sort of negates any energy benefit that you get from placing electrons in the bonding molecular orbital. So there's no incentive for helium to make a molecule, and that's why HE2 does not exist. Okay. So hopefully that makes sense. So usually, in general, if a molecule has all of the molecular orbitals occupied, it will usually not be stable. Now, you also remember about hybrid atomic orbitals, because without invoking something like hybridized atomic orbitals, you cannot explain the existence of simple things like methane, which I hope you believe in the existence of methane, because it does. But it's hard to believe that it exists. Why? Because look at the carbon electron configuration and the hydrogen electron configuration. Bonding happens according to valence bond theory. Remember, valence bond theory says you form a bond because two electrons of the same phase come together to have a constructive interference situation, and then that leads to a bond. But when you look at carbon, there's only two orbitals that have one electron each, and when you look at a hydrogen, of course you just have one electron in one s. So to make a bond, to mix two orbitals together, to combine two orbitals together to form a bond, you could imagine one of the 2p orbitals and one hydrogen combining to form a bond, because that would make two electrons, right? And then you could do the same with the second 2p orbital that has an electron in the carbon atom, but then that's it. You run out of an orbital that has just a single electron in it, which means you would think that carbon could only form two bonds, but we know for sure that carbon forms four bonds like methane, because we believe in methane. How does that happen? Well, that's called hybridization. To be able to form four bonds, carbon could promote one of the electrons from 2s orbitals to the p energy level, and then hybridize all those four orbitals, atomic orbitals that have one electron each. Then you can form four degenerate sp3 orbitals. It's called sp3 orbitals because you made these orbitals by mixing one of s and three of p orbitals. So it's quarter s in character and 3/4 or 75% p in character, these atomic orbitals. Right, so 75% p characteristic and 25% s characteristic. So it looks more like a p than a s orbital, this sp3 orbital, right, in the picture here. And so that's the orbital. So each of these is an sp3 orbital that has one electron each, and that pairs with an electron, single electron in the hydrogen 1s orbital, and that's how you form methane bonds. And I want you to notice how each bond, it's got two electrons each. You could have a situation where carbon might only form three hybridized orbitals. In the case of ethylene or ethene, that's the gas that actually is detected by fruits like banana to ripen, is an ethylene gas. It's actually a plant pheromone, considered a plant pheromone compound. But anyway, it has that structure as shown on the slide there. and it has a bond to carbon has a bond to 3 atoms, 2 hydrogens and 1 carbon. So it only needs 3 hybridized atomic orbitals, and to do so, the carbon only has to hybridize the s orbital and 2 of the p orbitals. And why can't you just use the 3 p orbitals, you might ask? Well, because you have to use the s orbital first, because s is lower in energy. Lower energy orbitals get used up first. So the 2s and 2 of the 2 p's. Hopefully that makes sense. So you make 3 degenerate sp2 orbitals, and these are called sp2 orbitals because you made them by mixing 2 of the p orbitals and 1 of the s orbitals. Now that leaves a peculiar situation. One of the 2 p orbitals of the original is left behind and left intact, and that's how the carbon in ethylene has 3 sp2 orbitals but 1 intact p orbital. Again, the red and blue just shows 2 phases of the 1 orbital. Okay. And so the ethylene compound looks kind of like this. Between the 2 carbons, you've got a sigma bond overlap of sp2 and an sp2 orbital of the carbons. So I want you to see that sigma bond in the middle. Remember, sigma just means the head-on overlap, right? Like tight overlap between the 2 heads. And but that leaves behind the p orbital each on carbon atoms that can form a pi bond, which is a side-to-side overlap of orbitals. It's not as strong as a head-to-head overlap. Therefore, pi bond is almost always weaker than a sigma bond. But because these 2 p orbitals, these 2 of the p orbitals on the 2 carbons have 1 electron each, they too can form a bond, right? And so that's what the pi bond is. And so in the Lewis structure, we would draw the double bond between the 2 carbons. One of those lines or bonds is a sigma bond, like we talked about, and the second one is actually a pi bond. So even though in the Lewis structure we draw these 2 identical lines as 2 bonds in a double bond, those 2 bonds look pretty different. Sigma bond here in the middle and the pi bond side-to-side overlap. You can apply the molecular orbital theory to p orbitals as well, and you can show the node in a bonding molecular orbital. Something like acetylene or ethine only has to have 2 bonds each, so you would make sp degenerate orbitals by mixing 1 of the s and 1 of the p's. That leaves behind 2 intact p orbitals. And so in acetylene or ethine, you got 2 p orbitals that are perpendicular to each other that are intact, and each of those can have side-to-side overlap or pi bonds, and so therefore the acetylene is said to have a triple bond, but one of those triple bonds here is a sigma bond, and the other 2 bonds are pi bonds. Hopefully that makes sense. And again, if you have questions about this, please ask during class.